Okay, so today what we're going to do is we're going to go over primarily a review of linear systems. Some of you may be very familiar with this, others it's newer, and so feel free to stop me if you have questions. You can just chime in as a small group and just turn on your audio and ask questions. So there's a lot of different objectives we're going to try to cover today. We're going to go over impulse responses and talk about why that's useful. We're going to look at signal expansions. We're going to describe and define linear systems, look at superposition, shift variance, and then talk about a little about convolution and do a few simple convolution things, really focusing on the convolutions that will be most useful for this class. So as Professor McVeigh talked about in the lecture, impulse response is a very important concept. And essentially, the impulse response is the way we characterize the system. So we imagine having a very small point object that we want to image. And so in this case, there's two little point objects shown on the left. And we go through our imaging system, and we end up with these blurred images. So those blurred images would be considered the impulse response. So we consider those little dots on the left, these dots as our impulses, and these blurred images would be our impulse response. And the really useful thing is if it's a linear system, then any input can be thought of as a weighted sum of these little impulses. And so the system response is just characterized by the sum of the impulse responses. These are some examples of what you might use for point stimulus. I know Professor McVeigh mentioned sometimes they just use the ball from a sort of like a ballpoint pen. Other ways you could do it is you could image a very thin wire, and essentially here is our stimulus, our physical stimulus. And this PSF stands for point spread function. So the other name for impulse response is point spread function. Here they're showing you both an isotropic and a non-isotropic point spread function. Okay, so let's get into a little bit about the math that we will use. So in this class, we'll primarily focus on both 1D and 2D Dirac delta functions. And so these are defined in the continuous domain. So delta of x is a 1D Dirac delta function. Delta xy is a 2D Dirac delta function. Some people use this 2 as a notation, but I think it's a bit redundant, so we probably won't use that 2 in the notation. If you see a delta xy, you sort of just should assume that it is a 2D Dirac delta function. Now, obviously, you can go into 3D or n-dimensional Dirac deltas, but we'll be primarily focusing on 1D and 2D Dirac delta functions in this course. Okay, so impulse response. So we're going to have our Dirac delta function, delta x. We're going to imagine it's the input to our system, and we're going to call our impulse response h of x. So for example, if this sort of a point object, the system could be an X-ray system, and the X-ray image of that point object would be our impulse response. Now, in general, we'll have some arbitrary function f of x, and we put it through our system, and we get the output g of x. And so that's an arbitrary object that we're going to image, say, with our X-ray system, and then we get our X-ray image of the object. So we want to be able to relate the impulse response, the response to delta x, to the response to any arbitrary input f of x. So that's really just sort of first pass at impulse response. We'll dive a little more into the Dirac delta function in a little bit. But before we do that, talk a little bit about signals and systems. So in this class, we will make distinction between discrete time or space and continuous time or space. Okay. So discrete functions are defined at discrete indices. So for example, 1D function s of n would be defined at all integer values of n, and a 2D discrete function sm comma n would be defined at discrete locations of the integers m and n. So for example, this here is an example of a discrete time signal. It's only defined at integer values. And here on the left is a 2D image, a very simple 2x2 image defined at integer values. So essentially everything we do in the digital domain, for example, even this computer screen, that is a discrete time signal in the sense that the way it's programmed is you're determining voxel values at discrete intervals of integers m and n. Okay, so your screen might be, say, 3000 by 2000 integer values. These are different locations. So when we're looking at our acquired image, the acquired data, that's always going to be discrete time because we're going to collect a finite number of values at discrete intervals, and that's what we're going to put into MATLAB or whatever program that we're going to use to reconstruct our image. And on the other hand, we'll use terminology like S of t or S of x for 1D continuous time signals or SXY for 2D. And so this is where we're using continuous time to sort of represent sort of the real world. So for example, this time series might be sort of part of a sound wave or part of a radio frequency wave that we're trying to look at. Or for imaging, the 2D object we're going to assume is defined over all space and continuously over X and Y, where X and Y are continuous variables. So a lot of this course is going to be saying, okay, we have some continuous object and we want to make a nice image of that. So we're going to go from continuous domain and we're going to make a discrete approximation of that continuous object. And one of the questions that we're getting into in the course, and we'll also cover in some additional sessions, is how do we do that? And that's related to this process of sampling. Okay, so let's get a little more back into some of the terminology we're going to use. We're going to take a little deeper dive into delta functions now. And there are two types of delta functions we'll deal with in the class. The first is what's called the Kronecker delta function. And this is what we do, we'll be working with when we're looking at discrete functions. So it has a very simple definition. Delta n equals 1 when the argument is n equals 0, and it's 0 otherwise. And it's only defined in integer values. Okay, so it's a discrete function, so it only has values on integers, and it's not defined anywhere else. And so, for example, this here is a picture of what delta n looks like. And you can sort of see it's just zeros at all the integer values, except for it's equal to 1 when n equals 0. Now, what you'll want to get used to is for imaging, we shift things around a lot. We either delay signals or we move images upwards and downwards or left and right. So you want to sort of get used to sort of what does it mean to have, for example, delta n minus 2. Okay, that's just going to shift the Kronecker delta function such that it now has a value of n of 1 at n equals 2. All right. Sometimes students get confused about this. The suggestion is anytime you're dealing with a problem, you have confusion, just ask yourself, when is the argument equal to 0? So n minus 2 equals 0 when n equals 2. All right, so no matter how complicated the problem gets, you can always sort of say, well, when does the argument equal 0? And that will tell you where sort of the important point is. So just as we have a 1D Kronecker delta function, it's useful to have 2D Kronecker delta functions. So this is delta m comma n equals 1 at the origin, m equals 0, n equals 0, and 0 otherwise. So once again, it's useful to look at shifted versions of that. So here is the Kronecker delta mn. And so this is the n-axis, and this is the m-axis, right? So I have delta m comma n minus 2. Now this has a value at n equals 2, because at n equals 2 is when this argument goes to 0. So if I have that argument on the second argument n, that shifts the Dirac delta up. If I have n minus 2, then that's going to shift it that way by 2 units. And if I have n minus 2, then it shifts it up 2 and over 2. Okay. So you'll want to just sort of make sure you're comfortable with this concept of shifting functions around in space. Okay, so the next really important concept to sort of have under your belt is this idea of discrete time signal or space signal expansion. So all this means is that we can take any arbitrary function, we'll just do 1D for now, any 1D function can be written as a sum of shifted Kronecker delta functions, each weighted by the value of the function. Okay. So let's look at an example. This is my function g of n. Okay. It has value of, let's see, -1 at the origin. It has value of 1 and -1 and a value of 2 here. Okay, so this is the origin 0. This is at -1 and this is at 1. Okay. So the way I've looked at, I've drawn it as just a bunch of discrete lines here. And so it's not too hard to sort of see that. You could write that as a sum of separate Kronecker delta functions. So for example, we clearly have something at delta of n, right? But we're gonna have to multiply it by a minus to get from here to here, okay? Sorry, so this is delta of n, and so this is the minus delta n minus 1. So that basically, so multiplying this by -1 gets me this term here. And then, sorry, this is 1.5. I have something at, oh, sorry, this, I think I made a mistake here. Let me see if I can get the eraser here. Let me just erase some things here. Okay, so actually this is the origin 0. I was confused. This is 1 and this is 2. Okay, so actually let me erase this as well. Okay, sorry about that. Okay, so this one here is just that direct, it just is the delta function. So that's this delta of n. Okay. And then we have this -1 delta n minus 1, so that's this term here. And then we have 1.5 delta n minus 2, so that's this term here. And so essentially, we can write this function g of n as just the sum of all these components on the left here, on the right here, sorry. Okay. And then we can do the same thing for 2D. So we can have a bunch of shifted 2D delta functions and we weight them appropriately and we can make any image we want. So for example, here's a 2D signal, A, B, C, D. And we are saying that we can break this A, B, C, D signal into a sum of something that just has an A, something that has a B, a C, and a D. And the sum of all those will give me our 2D signal. This is slightly different now. We have A, B, C, D, and we're going to show that we can write that as the sum of shifted and weighted Kronecker delta functions. So we have A times this delta function, B times this delta function, C times this delta function, and D times this delta function. Okay, so the way we write that mathematically is we say G of Mn is our image. It's A times this delta function, B times a shifted delta function, C times another shifted delta function, now that's shifted up, and D times the delta function shifted in both directions, right? And we can write that mathematically in this form here. Okay, so for example, if here's another image, and so we can write this. So this is like G, M, comma, N. And so we have a delta function at the origin plus 8 times a shifted delta function, M minus 1N, plus 5 times it shifted in both directions. And you can just sort of go forth and fill it out on your own, but that's the basic idea, that you can write any image as a sum of weighted and shifted delta functions. Okay, are there any questions up to this point? All right. Okay, so if there's no questions, then the next concept we want to review is the Dirac delta function, which is a little more complicated to deal with than the Sorry, let me get rid of this. Okay. Then the Kronecker delta function. So it's delta of x equals 0 when x is not equal 0. So it's not defined, it's defined as 0 everywhere except when x equals 0. But we don't really, it's not really defined at x equals 0. And it also has a special property that the area of this Dirac delta function is equal to 1. Okay, so it's a very strange function. And the way we can interpret this is we can interpret this as a rect function, a function that looks like a square here. So this function here has an area of 1, right? Because it has a base of 1 times the height of 1 equals 1. So this area here is, this height is 1. And we can imagine keeping that area the same, but as we shrink its width, okay, it's going to have to get taller and taller to keep an area of 1. So in the limit that this width goes to 0, that's essentially what our Dirac delta function is. We can also have 2D Dirac delta functions. And so this is defined as delta xy equals 0 everywhere except for the origin. And the area of a Dirac delta function is equal to 1. Okay, so it's not an ordinary function, it's what's called a generalized function. And just as in 1D, we can sort of assume, we can start off with something that has area of 1. So this is 1 by 1 by 1. Okay, so that would have an area of 1. And as we reduce the base, we let the height increase. And so the limit as tau goes to 0 is going to be this very spiky function in 2D. A very useful fact to keep in mind is that delta xy is actually just the product of delta x and delta y. Okay. So we'll see later that this is an example of what's called a separable function. So the most important property of the delta function is it's what's called the sifting property. Okay. That means if you integrate any function g of x with a shifted delta function, it just picks out the value of the function at the location of the delta function shift. And that's assuming that g of x is a smooth function. So pictorially, what it looks like is this. We have g of x as this smooth function that's varying. We come in and multiply it by this Dirac delta function, and then we compute the area of that multiplication. Okay, and since the area of a Dirac delta function is 1, that ends up just returning the value of my function g of x naught. So it's a good way of just sampling or picking out the value of function at a certain point. All right, so this process of multiplying by Dirac delta function and integrating is what's called the sifting property. Another useful fact is we'll also be dealing with sort of scale delta functions, so delta ax. And this has the interesting property that it acts as the delta function, right? Because ax equals 0 when x equals 0, but it's also going to have a sort of, its area is reduced. So imagine delta ax, if a is bigger than 1, is going to be narrower than delta x. And so it's going to have less area. And so that's the 1 over a. So this has less area. And area is reduced. That means for the sifting property, so for example, where a greater than 0, if delta ax, if we do the sifting property with delta ax gx, what that gives is it picks out, this is a delta function that has its action of 0. So it's going to pick out the value g of 0 and then multiply it by 1 over a. Okay, so why are we sort of spending so much time on delta functions? Well, one idea is that we want to now be able to express any function as a sort of integral of 1D delta function. And the way we do that is we say g of x is equal to every value g of xi times these shifted delta functions, delta of x minus xi d xi. Okay, and the intuition behind that is it's essentially what we did in the discrete domain. We're saying g of x is approximately equal to the sum of each of its values, g and delta x, multiplied by these little square functions. Okay, so that's shown here. We're going to try to approximate this function g of x. In the limit, we have all these little square functions that have the right height, and in the limit, they become these little spiky delta functions. We can do the same thing in 2D, where we can represent any 2D continuous function as the double integral of the shifted Dirac delta functions multiplied by appropriate weight. Okay, so that's for delta functions. And now that we have the framework of delta functions, we can define more rigorously what our impulse response will be. So the impulse response is going to be the response of the system over all space to Dirac delta function at a certain location. So for example, if we write our system L is equal to our system, then if I put in this Dirac delta function x1 minus I into my system, then my impulse response is just some function h of x2 comma I. And the reason we have an x1 and x2 is because our object might be in one location in some coordinate system, and our output might be another coordinate system, x2. So they're not necessarily the same coordinate system. Similarly, I can have a 2D impulse response function where I shift by minus I and minus eta. And so now I have my impulse response is h of x2 comma y2 colon xi eta. Okay, so we're going to go over two really important properties of the linear system and then do some examples. So there's two main properties that we want to review about linear system. One is addition and one is scaling. So linearity is fairly simple. If I have an input I1 and it goes through my system, so it's R of I, and let's assume it has some output K sub 1. I can imagine coming with some other input I of 2, it goes through the same system and I get an output K of 2. The linearity property means that if I come along with an input that's composed of I1 plus I2, then my output should be K1 plus K2. Okay, so if a system satisfies addition, it means that the response to any sum of inputs should be the response to the sum of the individual outputs. Okay, so when we're looking to see whether a system is linear or not, that is one of the things we need to look at. The other property it has to satisfy is scaling. Okay, so in this case, if I have an input I1, I put through my system and I get an output K1. Now if I come along and I scale I1 by A1, then if linearity is satisfied, then it means that it should the output should just be a scaled version of my original output. So then the output must be A1 times K1. So in general, we put those two things together. So system is linear if the response to weighted sum of inputs is the weighted sum of the outputs. So in this case, for example, I1 had an output K1 and I2 had an output K2. Now, if I come back with a weighted sum of inputs, so here I've multiplied A1 times I1 and A2 by I2, and then I've summed these two together, then if this system is linear, then the output must be A1 K1 plus A2 times K2. Okay.
I have a question. What exactly does the weighted sum of outputs mean? Why is it just not called the sum of outputs?
Okay, because the weights are because I've multiplied each output by a weight. So A1, so it's not, a sum of outputs would just be K1 plus K2, right? Because originally I had I1 go to K1 and I2 go to K2, right?
Okay, yeah.
So weighted sum just means I'm not just taking K1 and K2, I'm actually having to weight them by A1 and A2. Does that answer your question?
Yeah, understood. Thanks.
Great. Okay. Okay, so we're going to spend the next, maybe 10 minutes going through some examples. So why don't we do it this way? I haven't set up the poll. I'll probably do that next time. But just take a look at, so we're going to ask each of one, look at each of these. And so these are sort of the type of questions that could be asked, on a quiz or something. So here's one thing. So let's look at number A. So the question is A a linear system? So we have G of XY going in, I'm adding 10, and my output is G of XY plus 10. So go ahead and take a minute. And then if you just want to respond in the chat, just say yes or no. That'll be fine. I don't think I set up the poll for this yet. Well, maybe I did. Okay, yeah, actually, I'm going to launch a poll so we can actually do this. So just respond to the poll, whether you think this is a linear system or not. You guys all see the poll?
Yeah.
Okay, great. Okay, we're looking for one more person to respond. So if you haven't responded yet, go ahead and respond. We had 7 of 8 respond. Oh, actually, yeah. Okay, great. So everyone has responded. So here's the outcome. So 63% of you said yes. And yeah, so 5 of you said yes, and the other 3 said no. Okay, so let's take a look at that. And the way to sort of do these things is just go back to the definition. Does this satisfy additivity? Does it satisfy scaling? So let's look at both. So let's look at addition first. So if I have G, right, I know that it's going to go to G plus 10, right? And let's say I have some other input H. Well, according to the formula, that would go to H plus 10, right? And then if I come in with G plus H, that, according to the formula, would be G plus H plus 10. And the question is, does that equal the sum of these two? And it doesn't. So G plus 10 plus H plus 10 equals G plus H plus 20. Okay, so it doesn't satisfy addition, so it's definitely not linear. But let's actually go look at scaling. So let's say we know that G, oops, sorry about that. G goes to G plus 10. Let's say we come in with 2G, right? So that would go to 2G plus 10, right? And the question is, does that equal 2 times G plus 10? And that does not equal, because that's 2G plus 20. Okay, so in this case, the system is definitely not linear because it actually does not satisfy additivity, and it also does not satisfy the scaling property. All right. So are there any questions on that? Because there was quite a 5 of you sort of said it was linear. Any questions?
Could you go over the first part again? Just the additive?
Yeah, sure, happy to. Okay, so we know that if I put in G, I get G plus 10, right? That's just the definition of that system, right? It just adds 10 to whatever you put into it, right? And if I put in another input H, I'm just going to get H plus 10, right? Because that's another input, and we just add 10 to that. Now, if I come in with some other input, let's just call it G plus H, it's just an input. So it's just going to add 10 to that input. So it's going to be G, the output's going to be G plus H plus 10, right? So addition means that if I put in G plus H, I want to see what, and we know that G gave G plus 10 and H gave H plus 10. So if it satisfies addition, then it should just be the sum. This should just equal the sum of these two, right? And the sum of those two is G plus 10 plus H plus 10, which is equal to G plus H plus 20. So G plus H plus 10 does not equal G plus H plus 20. So therefore, it doesn't satisfy addition. Does that help clarify?
Yeah, I think I got that. I think what I didn't expect was maybe that H, I guess if you feed in a function H, and that is also supposed to give you H plus 10.
Yeah.
I just thought that only applies to this specific G of X, comma Y.
Oh, right. So G is just a name for something, right? So it doesn't matter what G is. G is just like the name of the function. So you can imagine G, you can replace G with anything, and it's always going to give you that thing plus 10. Okay. All right. So if there's no questions on that, let's go to the next question, which is B. So the question is this a linear system? Okay. Okay, last person, if you can respond, and then we'll. Great. Okay, so 7 out of 8 of you said it is linear. So let's take a look and see if it is linear or not. So in this case, if I put in G, I get 10G, right? So let's look about addition. If I put in H, I would get 10H. So if I put in G plus H, I should get 10G plus H, right? And that equals 10G plus 10H, sorry, H. So that does satisfy addition. So that's good. Now let's look at scaling. We said if we put in 10, we put in G, we get 10G. Now let's say I put in like 2G, right? Then, whoops, sorry about that. Then I would get 20G, right? And that just equals 2 times 10G. So it also satisfies scaling. So yes, that is a linear system. Okay. Any questions on that? Okay. Okay, so let's do this last example. C, is this a linear system? Great. Okay, so everyone's answered that. So 5 of you said no, and 3 of you said yes. So let's take a look at this. Okay, so this is a sort of a system that just takes an image and moves it up by 1 and over to the right by 1. Okay. So if we have G of XY, right, it just goes to G of X minus 1, Y minus 1, right? Similarly, if I had H of XY, it would just go to H of X minus 1, Y minus 1, right? So now let's say I've come in with some function G of XY plus H of XY, right? So now it's a sum of those two things. The thing, it just says shift that whole thing over by up by 1, right by 1. So that's basically going to shift both elements. And that equals the sum. It equals this sum. Okay. So it does satisfy addition. Okay. So if I have two things and if I have something and I shift it, and I have another thing and I shift it, if I have this two of them there, then the system shifts both of them. And so that satisfies addition. Similarly, if I just came and multiplied 2gxy, let's say multiply my xy, then that would just shift that whole thing. Okay, which is equal to 2 times my original output. Okay, so that all satisfies scaling. All right, so in this case, and that's good because we do a lot of translation and shifting things around in image space, and so it's actually nice that it satisfies linearity, because if it didn't, then that would be an issue. Okay, any questions on that? Okay, so let's work through. I don't know why it keeps doing that. Let's see, hold on. Okay. Let me just close the poll here. Fix things. Something about the poll kept moving things. Okay, so let's move on to example 2.2 from the class. So that was saying g of xy equals 2fxy. Right, and the question is this a linear system or not? And so here the question is, it's a little tricky, right? Because what is the input here, right? So essentially the way to think about it is your input is f, and you're multiplying it by 2, and you're getting out g equals 2 times f. Okay, so the xy is maybe a little confusing. It's not clear what the input is, but really, if you look at it as f times, the input is f, and you're multiplying by 2, and the output is g equals 2f. So the question is that a linear system? And as the example in the book shows, it is a linear system. And you know, it's useful to think about the way the book does it is it sort of does the addition and scaling at the same time. So we might think of lots of different inputs f sub I, right? And so we could write any arbitrary input as some wi f sub I, right? So that's doing addition and scaling at the same time. And so we know that if we put in, if this is my input, right? Okay. Then my output would be just 2 times wi f sub I. Okay. And then this could just be written as 2 times wi to fi. Okay, or sorry, let's, so each of those, oops, sorry about that. So for example, if let's add f1, that went to 2f1, f2 would go to 2f2, and so on and so forth. Sorry, w1, w2. Sorry, let's erase that. Okay, so basically now we have that this is still the sum. So the sum, it's got the sum and the scaling property built into it because we have each, these are the individual outputs, right? So we can say that our output is just going to be a weighted, so this is the sum, and these are the weights. Right, so that is a weighted sum of my individual output. So that is a linear system. We'll come back later to see if it satisfies shift and variance, but for now, that is a linear system. Okay, so linear. All right, any questions on that? Let's look at the next example. Let's see. So this is example 2.3. G of xy equals xy f of xy. So once again, we can think of putting in an input f, and it's going to go through our system, and the output will be xy times f. Okay, So now the question is this is a linear system. And so once again, we can consider an input, Wi, Fi. Okay. And the output would then be X, Y times Wi, Fi. And we can put the XY back in here just so it's explicit. Okay. So that can also be written as, since we're summing over i's, we can bring the XY in it. So that's going to be Wi, XY, Fi, X, comma, Y. And these are the individual outputs, right? These are the weights. And this is the sum. So once again, we have a weighted sum of individual outputs. And so this will also be a linear system. And we'll come back and look at the shift invariance of that in a minute. So any questions on those two examples in terms of linearity?
Yeah, so I'm trying to understand in the book example why, like in both of these examples here, I think they go from like, so let's say in example 2.2, if we're looking at the sum of the weights times 2f xy, it comes, the next step is that 2f becomes g. And I'm just trying to understand
Okay.
what's going on there.
Yeah, so basically the 2fi, so basically each of these outputs, right? So if I put some arbitrary input fi, I'm going to get 2fi out as the output, right? But I could also just call this g sub I, right? That's just, g sub I is just the output to some input f sub I. So they're just substituting, they're just saying 2fi, I could also call that g of I, right? Because that's my function. My function is just like a name, right? I could call it anything. So if I have something that's 2 times f or 2 times, anything, it could be 2 times h, I'm just going to call that g.
Cool, thanks.
Okay, great. Any other questions? Okay, so a lot of this is, yeah, I mean, especially when you're dealing, as we do the math, it's useful to think of these functions as just sort of, there's nothing special about G or F. It's just a name. I could call it Joe and Harry or something like that. Okay, so they're just names. Okay, so the next thing we're going to talk about is superposition, and we're just going to go through this relatively quickly in the interest of time. The point is that we've already said that we can write any function, let's say a 1D function g of m, as a weighted sum of delta functions. Okay. Now the question is, and then we can also say that we have, we can define the impulse response to any shifted delta function by its impulse response h of m prime comma k. All right. And so now the question is, what is my response y of m to any arbitrary g of m? Okay. And so the way we'd go about doing that is as follows. I'll just sort of map out what we do. We say we first replace, we keep our L, that's our system, and we're going to write it as, g of, let's see, let's write this, let's call it g of k, delta m minus k. Okay, so that's just this written in summation notation, right? I have a g of k times a delta function shifted by k. So that's g of 0. There's a shift of 0 here. G of 1 shifted by 1. G of 2 shifted by 2. Okay. Now, since it's a linear system, I can bring that L all the way in because I know that the response to a weighted sum of to a sum of inputs is just the sum of those outputs. So I can certainly write that this is equal to this, right? L of g of k delta n minus k, All right, so I can bring the L, since it's a linear system, I can bring the L inside the summation. And the next thing I can do is, because of scaling, I can go past this scaling term. And so I can write that equals G of K L of delta M minus K. Right. And now I just have G of K times each of my impulse responses. So superposition is just saying, if I know all my impulse responses, then given any arbitrary input, I can express it as the sum of those weighted impulse responses. And so then I can write out what the output is as just a sum. This is just a weighted sum of these impulse responses. So, and that's shown here in the bottom as well. And this just goes through the math a little more in detail. Okay. We can do the same thing with any arbitrary function in 2D, for example. Okay. So it turns out that if I can write any 2D function, remember, as a sum, or in this case, double integral of shifted Dirac delta functions. And so the response turns out to be just a bunch of these, the impulse responses weighted by these values G. And then in this case, the double summation is replaced by a double integral. But it's the same idea that if I know the different impulse responses, then I can just sum everything up and weight them, sum up the weighted impulse responses. Okay, so that's really superposition, which we're not going to talk about too much, simply because we're going to move forward towards convolution. And therefore, we need to introduce a new concept called space invariance or shift invariance. Okay, so the other term we'll use for this is shift invariance. And what this means is, the physical picture of this is, if I have an object and it gives some response here, if I shift that object, then my response should just be shifted. Okay, so that's a special property. It's not true of all systems, but it is true of some systems. So for example, if you had a bell and you rang it, and you hit it in a certain way, so if you just hit it, that's your impulse, and the bell would ring. And you would hope that if that bell is shift invariance, it means if I come back tomorrow and hit it exactly the same way, it should ring exactly the same way. So that's what shift invariance means in time. In space, it just means that if I have a camera, for example, and I put my object here, and I get a picture, and then I move my object over here, and I get another picture, that picture, the image that I see should just be shifted. Okay. So, so that's what shift invariance is. So the nice thing about a linear shift invariance system is that means that I only need one impulse response, because it means the impulse response doesn't depend on where the impulse was. So in this case, I have some input shown here on the top, and I only need one impulse response now because it's shift invariant, right? If it wasn't shift invariant, then for every impulse, I would need a different impulse response. But because it is shift invariant, I only need one impulse response. And that means that I can now look at the response to this impulse. And then I can look at this next impulse is multiplied by 2. So I have to multiply its impulse response by 2, but it's the same shape. And then I can look at the response of this impulse, and it's the same height as the first one. So its response to the same height. And the output to the whole system would be the sum of all these. Okay, so because it's a linear system, I can just take the sum to all those impulses, It's just the same impulse response for every impulse. And because it's linear, I can just sum them all up. Okay, so that's what really a linear shift invariant system buys you. So the output is now the weighted sum of shifted impulse responses. So what does that allow us to do? Well, remember before we're saying that this response to any shifted impulse can be written as h of m prime minus k. Okay. So we can play the same game. We said that G, so we take our linear system L, it's just a weighted sum, G of k of delta m minus k, right? And we can take the summation all the way into the middle, past the summation, past the scaling, and we have delta of m minus k. So these are the responses to every shifted, we're taking the response of the system to these shifted impulses, right? Because it's shift invariant, we know that our output is just going to be a shifted versions of the same impulse. So g of k, h of m minus k. Okay, and so that's essentially what convolution is. So convolution is going to be a very useful concept throughout the course, and there's a very deep relationship between convolution and Fourier transforms, and we'll make use of that. Today, I just really want to give you some of the basics on how to look at convolution and some basic convolutions that we'll be working with. The intuition is still really what we dealt with in sort of that example we just did, where the shift invariance allows us to just use one impulse response, and the output of our system is a sum of those shifted impulse responses. So these are basically the shifted impulse responses. Okay. So the output is now the weighted sum of shifted impulse responses. This is just writing it out again so you can see it. So now we're going to get into a little bit of the mechanics. This really isn't going to be a course about how to do convolution, but I'm going to just show you what it is, and then so you have some concept of it. But then I'm going to sort of point you to what are the most useful convolutions to have that we will use in the course that are useful to just know, and so that they won't be too hard to remember. So we do want to introduce those. So this is this integral here is what's called the convolution integral. And typically the way we write it is we'll have g, and then this is the convolution symbol asterisk h of x. So it's not multiplication. So just make sure that whenever you see sort of that asterisk symbol in this course, we're talking about convolution. We're not talking about multiplication. Okay. So let's take a look at this integral in a little more detail. So if I have a function g and a function h, right, and I want to convolve g with h, this formula here is telling me how to do that. It says take my function g and evaluate some values I, take h and see it has a minus I, and sometimes I have to flip the function, right, because it's a minus I argument, and then I'm going to shift it by some argument x. Then I'm going to take those two things and I'm going to multiply them together. So two functions, one is the g, one is the flipped and shifted version of h. I'm going to multiply those two together, and I'm going to integrate that product. So we'll go through an example of that just so you see how it's done. But one super useful fact that you should definitely remember for this course is if I take any function g of x, and we'll assume that this is a nice smooth function, and I convolve it with delta of x minus delta, that has the very interesting property from the sifting theorem that just gives you g of x minus delta. That's a super useful thing to do. That means that I can represent shifting things around by just convolution with a shifted Dirac delta function. Okay. So let's use that as an example. So let's say that this is my function, this is the rect function. So this is rect of x. Okay. I don't remember, did Professor McVeigh already present rect of x in lecture? Was that?
Yeah.
You did great. Okay, so rect of x is going to be, oh, that's right, because we did rect and sync. So rect of x and all scaled versions of rect of x is going to be super important. So that's one of those functions that you just want to get used to. We'll use rect all the time. So the question is, what is rect of x convolved with? So we have rect of x convolved with delta of x plus 3/4 plus delta x minus 1/4. Okay. So that could look a little bit intimidating, but the answer is very simple. It's just I'm going to take rect of x and shift it to be centered around those Dirac delta functions. So first we'll write down the solution analytically, and then we'll draw it out. Okay. So that is just rect. So this is convolution. Rect of x plus 3/4 plus rect of x minus 1/4. Okay, so the solution is very simple. Essentially, you can just take your function and replace its argument by the argument of the Dirac delta function. So what does that look like? Well, it means I'm going to have, let's say this is 1 minus 1 and 1. So this is 3/4. Okay, I'm going to have one rect function that's centered around 3/4. So it's going to go like this. So it's going to go from minus 1/4 to minus 5/4. Is that right? Yeah. And then I have another rect function that's centered around 1/4. So it's going to look like this. Okay. So that's what that rect function does. And if we want to get really fancy, we could write this as a rect function. It's centered around minus 1/4. And it's got a width of 2. So we're going to divide it by 2. All right. So it's basically those two rect functions put together just makes another rect function that's both shifted and scaled. So so definitely commit this to memory. That is a very useful fact that we will use throughout the quarter. Okay, any questions on that?
Just that last step, how do we simplify it into rect x plus 1/4/2?
Yeah, that's a great question. So, and this is sort of, you know, being able to sort of scale functions is a useful skill to have. So so we have these two rect functions, and the center of the rect function is here, right? At minus, so of this big rect function, the center is definitely at minus 1/4. Do you agree with that? Right, because you have two rect functions.
Okay.
So we know we need to have something x plus 1/4, right? Because then we know that x plus 1/4 equals 0 when x equals minus 1/4, right?
Okay, yeah.
Okay. So now the next thing is figuring out, well, what is the width? You know, how do I get this 2 here, right? Well, here's the thing. Like if I have rect of x has a width of 1, right?
Mm-hmm.
So what is rect of x over 2? What's the width of rect of x over 2? What's the width of that?
That's 1. That's going to be 1.
That's going to have a width of 2, right? And the way to think about, so I'm going to tell you the way to think about that, because it is confusing, right? And you just sort of guess at it. You'll jump, you know, you might get it right, but you might get it wrong. So let me just tell you what a good way to do it is. So you know that rect, the points of rect are 1/2 and a minus 1/2, right? Because rect is only defined from minus 1/2 to 1/2, right? So that's rect of x, right? So now it looks like rect of x goes. So if I want to know what the edges of rect of x over 2 is, I want to ask myself the question, when does x over 2 equal 1/2? Well, that's when x equals 1, right?
Yeah.
And similarly, x of 2 equals minus 1/2 when x equals minus 1. So then the way I would draw a rect of x over 2 is it would go from minus 1 to 1 and have value of 1, right? So now the width, so you can sort of see the width of that is 2 now, right?
Yep, I see it now.
Okay, so that's why I have this 2 down here. Because the width of this, right, is 2, right?
Yep.
If you want to check it, you know, you can sort of see that this is x of 3/4, right? So for example, I could plug in and say x, let's see if my answer is correct. X plus 1/4 over 2 should equal 1/2, right?
Mm-hmm.
Or when does that, well, the question is, when does that equal 1/2? Well, if I solve this for x, I'll get x equals 2 times 1/2 is 1, 1 minus 1/4 is 3/4. So x equals 3/4. So that's the right endpoint.
Got it.
Okay, so if you ever get confused, you can always ask yourself, when does the argument to the rect function equal 1/2 or minus 1/2? And that will always let you check and make sure you've got it correct.
Thank you.
Okay, great. So now here's a slightly more complicated convolution, right? Now I have two continuous functions, rectangle functions, and I'm convolving them with each other, okay? So this, you may or may not know the answer to this. I don't expect you to know the answer to this if you haven't had convolution before, but it turns out, and what we're going to derive is the answer looks like this. And this is what's called a triangle function. And we can write it as delta lambda of x, okay? So we may or may not use this too much in the class, but it is useful just to sort of see how you might go around it, because it gives you slightly more insight into convolution. So remember, for convolution, we're taking one function g of I. So in this case, it's the rect function. We're taking the other function and we're flipping it and shifting it, okay? And the shifts is determined by x, okay? And we take those two functions and we multiply them together here, and then we want to integrate over that. So let's look at this. So in this case, obviously x equals 0, right? Because this is 0. So I have a rect function. If h of xi is rect function, then h of minus I is just a flipped version of that rect function, right? So it looks the same. I multiply these two rect functions together, I get another rect function, and then I integrate until the area is equal to 1, right? Because the area of rect function is just equal to 1. So that's nice. So basically, if I keep track of things, I know at 0, I get a value of 1. Okay. Now I'm going to go to another x location, x equals 1. Okay, so I want to plug in the value for 1 here. Okay. So now I have h of 1 minus xi. So that's sort of interesting. So I basically taken my rect function, I flip it around, and then I shift it over by 1 whole unit, right? Okay. And this is a rect function centered around 1 now, right? Because 1 minus xi equals 0 when xi equals 1, right? Now I look at those two rect functions. This ends at a half and this begins at a half. So when I multiply those two together, I get nothing, right? So the area here is equal to 0. So I know here I would plug in this. I had 1 here and I have 0 here, okay? And then here is x equals 1/2. So now I've just shifted that rect function over by a half. Okay, that flipped rect function shifted over by a half. And so now the overlap is just this. So it's half of a rect function. So now the area is 1/2. And so I know here I'd have a half. And so that's where I get the triangle. It's just like that, and it's symmetric. So it looks like that. So that's sort of if you ever have to do a brute force convolution, that's what it would look like. Okay. But we're not really going to emphasize it too much in this course, just so some background so you have it. We will certainly emphasize convolution with direct delta functions, so make sure you have that under your belt. 2D convolution we will definitely use in this course, but once again, it's going to be mostly convolution with direct delta functions. So sometimes we will denote 2D convolution as star star, and just means we're using 2 coordinates. But if everything has, obviously it's an XY coordinates, then we will sometimes abbreviate with just 1 star because it's understood it's a 2D convolution. Okay, so let's do an example of that because it is useful to think about how we would apply this in 2D. So here we have a 2-dimensional rect function, rect of x comma y. And we say we want to convolve it with this sum of shifted direct delta functions. Okay. So what is that going to do? Remember, convolving with a direct delta function just takes your object and moves it to the location. So essentially, if we want to write this out, we would say g convolved with h is just going to be equal to rect of x plus 1/2 y, because that's shifting it to this delta function, plus rect of xy, right? Which is because this direct delta function is centered at the origin, so it doesn't move the rect function at all. So this rect of xy gives me this part here, right? And this rect of x gives me this part. Okay. So those are two rect functions and they overlap each other. And so I know I need to sum them up too, right? So the value here where it's blue, that's 1, because I only have a 1 rect function there. The value here is 2, and the value here is 1 again. Okay, so that's about as complicated as we're going to get for 2D convolution in terms of manually doing it, because it's sort of a lot of algebra to do 2D convolution by hand. So anything more complicated than just shifting things around with direct delta functions, we will typically let you use MATLAB to do the 2D convolution. But this is useful, sort of understanding this simple concept is useful for understanding what MATLAB is doing. Okay. So for example, here's, I believe this is what you did for homework 1, is that right? And let's think about how we might think about this in terms of what we just did. So let's say this is sort of the counterpart of my h function, right? It's some sort of Gaussian function in 2D, right? It's a 2D Gaussian function, right? And we can think of this cross here, we can think of as being made up of, if I zoom in on this, right? Let's say we zoom in on this. I can think of this as being just a bunch of little delta functions, right? I could certainly make this up out of lots of little dots, right? Right. So I know that if I convolve each of those dots with this thing, it's just going to move that blur to where the dot is. And so I can think of this function here on the right is just made up of, there's going to be a blur, a shifted blur here, a shifted blur here, a shifted blur here. So that overall blurred cross is just made up of a bunch of those shifted, addition of all those shifted blurred functions. All right, so that's how you can think about, one way you can think about convolution. And obviously if I make that blurring fatter, then now each shifted blurred version of that, and I add all those up, is going to give me a much more blurred version of the cross. Okay, there's something in the chat here. Thank you. Okay, someone has to leave. That's fine. So this will be recorded. So if someone needs to, okay. So we're going to stop there, and what we'll do is we'll go back and first see. So next time we'll do Fourier transforms. I think this is a good place to stop for today. But next time we'll talk about 1D and 2D Fourier transforms. And then if we need to, we'll add a third supplementary session to cover any material that's not covered, and then also talk about sampling. So are there any questions before? I'm going to go back and look at the examples 2.2 and 2.3 in terms of shift and variance to see if they're shift and variant, but I just want to see if there's any questions before we go through those examples. Okay. If not, let's just go back to where those things are. It's probably a faster way to do this. Okay. So example 2.2, we already looked at the linearity of this, right? So now we want to look at shift and variance, right? So remember, we said that if I put in F, I get 2F, right? So now the question is, if I put in a shifted version of F, do I get a shifted version of the output? Okay. So for example, if I put in F of X minus X naught, Y minus Y naught, then according to my formula, the function will just return 2 times F X minus X naught, Y minus Y naught, right? And my original output was just 2 times F of X, Y. So this is definitely just a shifted version of my original output. So that does satisfy shift and variance. All right. But now let's look at this one here. So here, if I put in F of X, Y, I'm going to get out X, Y, F of X, Y, right? Now let's say I put in F of X minus X naught, Y minus Y naught. It gives me X of Y. It just takes my input and multiplies by XY, which is F X minus X naught, Y minus Y naught. Okay. But now if I look at a shifted version of this, if I shift that, I have to shift all the XY things. So shifting this, I would have to have X minus X naught, Y minus Y naught, F X minus X naught, Y minus Y naught. And these two things are not equal. Okay, so that's not shift invariant. All right, so any questions on that or anything about linear systems, shift invariance that we have about 9 more minutes, so we could, if you have any questions at all, we can answer them now, otherwise, but we can conclude it. Okay, so I'm not hearing anything, so thanks for attending the supplementary session. It is recorded, also I'll post that in a minute. If you are interested in some review of Fourier theory, then we'll start that next time, but I think it's too late to start that right now. All right, have a good weekend and we'll see you in class.